Okay, so we're working on these four problems. Page 78, number 4, 7, 8, and 9. Everybody have a homework? Who handed in a homework? Preferably their own. Okay, let me just start with 4 for a second. What's the diameter of a graph? It's over all distances between two vertices, it's the longest one. So we have a graph, we look at every pair of vertices, and we find the longest distance. And here, we're told that the diameter of G complement, if G is a disconnected graph, then in fact the diameter is less than or equal to 2. So what that means is you got to show that in the complement, every pair of points is either joined by an edge or joined by a path of length 2. Okay.
Certainly, we're supposed to prove that the diameter is less than or equal to 2. It's the pair of vertices with the shortest apart, the biggest distance. So the distance is like the shortest path. When one is the longest shortest path.
That's exactly it. What is the shortest, longest path?
So what's the longest shortest path?
Longest, shortest path.
I'll get to what's the longest. So the distance between two vertices is the shortest path. And the diameter is the length of the path between two vertices whose distance is the greatest. What that means is their shortest path is longer than any of the other shortest paths in the world.
Okay, if that makes sense, let's start with number 4. Let's start with number 4. Okay, so what we're told is that G is disconnected. G is disconnected. So what does it mean to be disconnected? So for some pair of vertices, there's no path between them. Okay? So another way of looking at it is that the graph comes in pieces. Okay? So the graph, we can partition the vertices into pieces. This is a connected component, this is a connected component, this is a connected component. It's disconnected, so there's at least 2 of these. Okay? So there's at least 2. All right. Now what's the complement? If a graph is disconnected, what can you tell me about the complement? Let's just look at 2 components. What can you tell me about the complement? Do what? Much more than connected. Much more. Okay, it's disconnected. The graph is disconnected. This is G. What can you tell me about the complement of G? It certainly has the same vertices. What else? In the complement, every vertex here must be adjacent to every vertex here. Is that clear? Okay, so now let's prove this. So G is a disconnected graph. So G has at least 2 components, and it may have more. So what do I have to show? To show that the diameter is less than or equal to 2? To show that the diameter is less than or equal to 2, I need to do what? I need to pick 2 vertices and show in the complement that what's the distance between them? At most 2. Pick 2 vertices and show that the distance between them is at most 2. Okay, so one more time. Here's the graph G. Okay, so what are the possibilities? I'm going to close your eyes and pick 2 vertices. Tell me the possibilities for where these 2 vertices could lie. That's kind of a vague question. So here's G. It's disconnected. I'm going to pick 2 vertices. There's 2 possibilities. Either the 2 vertices are in the same piece, or they're not. Okay, one more time. Either the 2 vertices are in the same piece, or they're not in the same piece. Okay? So those are the only 2 possibilities. Right? Here's G. I pick 2 vertices. X and Y. So one possibility is X and Y are in, let's do the easiest one first, are in different components. Different components of G. Different components of G. Okay, so let's imagine I close my eyes, I pick a vertex here and a vertex here. If X and Y lie in different components of G, X and Y are in different components of G, then what can you tell me about what happens in G complement? Do what? More than. So we got to be careful when we say connected versus. What?
Did you say path?
No, more than a path. Adjacent. Okay, there's a difference between connected and adjacent, right? Connected just means that there's a path. This is a very special path. If I take 2 vertices in different components, then in the complement, they're adjacent. Okay, if X and Y are in different components of G, then the distance, I'll get it. The distance, does he use DIST? The distance from X to Y in G complement, notice this is in G complement, what's the distance from x to y? What's the length of the shortest path between x and y? 1. Okay? All right, so what's the other possibility? I'm claiming there's only two possibilities. X and y are in different components, or they're in the same component. If x and y are in the same component. Of G. Okay, now it's important that this was a disconnected graph, and there are at least two components, two non-trivial components. So let's imagine x and y are in the same component. If x and y are in the same component. Now this is G. So these little blobs here are non-trivial components of G. So I know that here there is at least one point. Okay? Is that clear? Now, in the complement, this is G, what can you tell me, let's call this Z, what can you tell me about what happens in the complement between Z and X and Z and Y? X is connected to Z, not connected, sorry, you be careful, X is adjacent. X is adjacent to Z, and what? Y is adjacent to Z. So what I know is if X and Y are in the same component, then the distance from X to Y is less than or equal to, what's the length of the shortest path from X to Y? Okay, is less than or equal to 2. Why is it less than or equal to 2? What if X and Y were non-adjacent in this component here? In this component of G, if X and Y were non-adjacent, then in the complement they would be adjacent. And in fact, the distance between X and Y in the complement would be 1. Okay, but it doesn't really matter. I'm just trying to show that the distance between any 2 points is at most 2. Is that clear? Is the proof clear?
Yes.
Okay? And again, I can't encourage you enough to draw a picture, but a proof is not, don't give me a proof by picture. Okay, a picture is good as a sort of a roadmap to how you're going to prove something. So you have this little picture, and now I'm going to take a look at all the different cases. Okay? All right.
So distance used in this question is the ID.
Sorry, what?
The distance used in the questions is
The diameter.
that is the same.
That's the same. Yeah. So the diameter is the longest distance between 2 points. What we've shown is the distance between any 2 points. If they're in different components, the distance is 1. If they're in the same component, the distance is less than or equal to 2. And this is important. So between every pair of points, the distance is less than or equal to 2. So the diameter of G is less than or equal to 2. Okay. Is that clear? Don't let me get away with cheating. Right? If the book asks for something, make sure that I say everything that I'm supposed to say. So you do know the video is available for everybody. Okay, all right, because you don't have to take pictures. You can get on the video and then you know you can watch it. You can stop it. Okay. But take pictures if you want. Okay. Number all non-isomorphic four regular graphs of order 7. Anybody got 1? 4 regular graph of order 7. You don't have one?
我找每句都可以。
Okay, so degree 4, degree 4, degree 4, degree 4. What's the degree of that one? Careful who you're taking off. Oh, okay, yeah. Okay. Now you're okay.
所以定下来，说一定会所以相应，所以这个人物呢，本身只需要再分两个，然后来找其中一个可能的东西。
The Boulder book still carries the book?
No.
Oh.
And you would just, and you just do it down at your screen.
Okay, does anybody have one 4 regular graph of order 7? Anybody have 2? So how might you? We're not gonna belabor this, but how might you figure out a way to catalog without looking at the atlas of graphs? By the way, there is an atlas of graphs that actually has all the probably 4 regular graphs of order 7. How can we actually figure out how to construct all these? How would you go about it?
Try to list out the graphs one by one.
Say that again?
Try to list the graphs.
Okay, so come up with some sort of method to list all the graphs.
So start with a point, and because it's a 4 regular graph, so yeah. just
Okay,
like
so
this.
start with a vertex at degree 4.
Yeah,
How many more vertices are there?
2.
2. Now, again, we're not going to go through all these steps, but what you might do is say, okay, now what is the possibility about the number of edges from these 2 points to this set? Okay, can these 2 points send all their edges up to this set? So can, for example, is that possible? Now remember, we need a 4 regular graph. Is this 4 regular? Not yet. But some of the vertices have degree 4. These 3 vertices have degree 4. So these 4 vertices have degree 3. So I need to increase the degrees of each of these 4 vertices by 1. So here's 1. Okay. Is there another one? Maybe this is the only one. Let me back up a second. These 2 vertices down here, the possibility for these 2 vertices, either they're adjacent or they're not. Okay? If they're not adjacent, then we knew that all 4 of their edges must go up to this set of 4. So this is the only graph on 7 vertices that's 4 regular where these 2 points are non-adjacent. Is that clear? Okay. So the only other possibility is that we have 2 points down here and they are adjacent. Okay, so now how many more adjacencies does this vertex here need? 3 more. And almost randomly we'll put those in. This guy is done, this guy is done. Now I need to add 3 more vertices, 3 more adjacencies to this one. So the possibility is it goes to the same 3 vertices. I'll let you figure that one out. Or it goes to a different set of 3 vertices. If it goes to a different set of 3 vertices, it overlaps in 2 of them. So I'll draw that. Okay, so this has degree 4, this has degree 4, this has degree 4. 2, 3, 2. 2, 3, 2. So let's see. Now we have all degree 4. It's don't take this the wrong way and never say this outside of this room. It's like a game. You're playing a game, trying to come up with the condition that the book asks for. Problem like this, it's just a matter of now looking at any other possibility. If this is not adjacent, we're done. If this is adjacent, then we have to look at other possibilities. Okay? And now your job is to show that we have them all. Okay? We run out of all the possibilities on these seven vertices. Okay? I'll leave that to you to actually list them out. And on Tuesday, someone will tell me exactly how many 4 regular graphs on 7 vertices there are. How many different 4 regular graphs of 7 vertices there are. Okay, how many non-isomorphic graphs are there with degree sequence 5, 5, 4? Okay, so let me back up. A degree sequence. So if I have a graph G, and with vertices V1, V2, Vn, so I have a graph and I have a vertex set V1 through Vn, then the degree of V1, the degree of V2, the degree of Vn is called the degree sequence. Okay, so it's simply a list of the degrees of the graph, of all the degrees of the graph, and it includes repeats. So for example, in this case, 5, 5, 4, 4, 4, 4. 5, 5, 4, 4, 4, 4. Okay, how many non-isomorphic graphs are there with this degree sequence? So there's my degree sequence. 2 5s and 4 4s. Let me back up for a second. I just want to make sure we're all paying attention. How many graphs are there with this degree sequence?
0.
Why 0?
The sum of the degrees is not even.
Very good. Because the sum of the degrees is not even. Or notice there is an odd number of odd degree points. If we have an odd number of odds adds up to an odd. And then add evens doesn't change that. Okay, so that one's easy. Problem is that's not the problem that he gave us. They gave us this problem. We did 5, 5, 4. No. That's a different one. 5, 5, 5, 4, 4, 3.
Oh, we just did that.
No, when I took 4 away. No.
Oh.
Sorry. Yeah. Okay. Okay, does anybody have 1, 5, 5, 4, 4, 4, 4? Now this is graphs, so there's no multi-edges, and we're not allowing loops. And I'm just going to keep talking. So if there is a graph like this, how many vertices does it have to have? 6 vertices. So what can you tell me about the vertices of degree 5?
So they are adjacent to all the vertices.
All of the other vertices,
Yeah.
including the other 5. So we know if this exists, we know that's the start. We know that's the start. Now, what's the 4 degrees down below? What are these? These degrees have to be what? These degrees have to be 4s. So if I cover this up, these degrees have to be 2. Okay, so I need a 2 regular graph on 4 vertices. I'm not allowing multiple edges, so I'm not allowing 2 edges between 2 points, and I'm not allowing loops. So I need a 2 regular graph on 4 vertices. There's only one. The only 2 regular graph on 4 vertices looks like that. So the answer to the question, how many non-isomorphic graphs are there with degree sequence 5, 5, 4, 4, 4, 4, 4, 4, 4, is 1. Okay, what about number 9? 5, 5, 5, 4, 4, 3. It's like a phone number. Okay, 5, 5, 5, 5, 5, 5, 4, 4, 3. How many vertices are there in this graph? 6 vertices. So what can you tell me about the vertices of degree 5?
So they're adjacent to all of
They're adjacent to all the other vertices. So here are the 3 vertices of degree 5, and they must be adjacent to not only themselves. Now, the 3 vertices of degree 5 are adjacent to one another. There's 3 more vertices. So now these have degree 5, and the degree of these vertices is, at this point, the degree of these 3 vertices here is
3, 3,
3. 3,
3.
3, 3. But I need 3 5s, a 4, 4, and a 3. Okay. Now, the nice thing about both of these is they're the only such graphs. There aren't too many graphs that are uniquely, there aren't too many sequences that are uniquely realizable. So just to put the definition down, if I have a degree sequence, and usually we order them. So I have a degree sequence with degrees D1 through Dn. We talk about a realization. Realization is a graph with degree sequence, and I'm just going to call this sequence D, sequence D. And again, we usually order them from largest to smallest. So a realization is a graph with degree sequence exactly D. And if there's only one, we call the sequence S is uniquely realizable. If S is realized by only one graph. Okay, so lots of definitions. Lots of definitions. Some we'll use often, some we won't use too often. Okay? Okay, I think there's. I'll let you play with that. I was going to ask you to do 11, but that's just a waste of time. We're just. Okay, so we got degree sequences. Now we talk about a degree sequence as being graphic, just like I said over there, if there is a realization. If there is a realization. Okay, Okay, so we call a degree sequence, we call a sequence graphic if there's a realization, realizing those as the sequence of degrees. So it's a realization. So I'm going to give you a sequence of degrees. So I'm going to give you some degrees. Okay, I'm going to give you a sequence of n degrees. So D1 greater than or equal to D2 greater than or equal to D3. So here's a sequence of non-increasing. Okay, so we always read from left to right. So it's non-increasing sequence of integers, of non-negative integers. Okay, so I have a sequence of non-negative integers. For example, 5, 5, 4, 4, 4. Let me put another one. Here's another one. 5, 5, 4, 4, 4, 4. Here's another sequence. 5, 5, 4, 4, 4, 3. Obviously, there are many. There are many sequences. The question is, which of these sequences are realizable? Which sequence can you realize? Now, we don't know much about graphs yet. We're only getting to the end of the first sort of introductory part. But let me ask a question. This sequence here, without even trying to draw it, don't even try and draw it. What do you know about the vertices of odd degree? What do you know about, you told me before, what do you know about the sum of the degrees?
It has to be 2 times edges.
It has to be twice so the sum of the degrees must be twice the number of edges, so it must be even.
Yeah.
Must be even? What's the sum of these degrees? Odd. So is this realizable? No. Okay. So don't forget, that's the easy one. Check that first. Okay, so is a sequence like this realizable? So, and this is a problem that existed for quite some time. I'm going to go back to some of the history. The Königsberg Bridge problem was first written by Euler probably around 1736 is a date that's given to it. I mean, that's, I don't know. You never know how true that is. Okay, but let's sometime in the 1700s. They didn't know much about graphs and degrees, and it was over the next, now it's almost 300 years, 280 years, that we've developed more and more theory about this idea of these structures that we call graphs. So, here's a sequence. This is a non-increasing sequence of integers, non-negative integers. Right? At some point, if you want to talk about negative degrees, there's plenty of stuff that you can read about that. But we're not going to deal with that. We're just dealing with basic graphs. So here is a non-increasing sequence of non-increasing. So nothing over there is greater than anything over here. Non-increasing sequence of integers. Is this sequence is D1 through Dn a sequence of degrees for some graph? problem that was around for a long time. Basically, I know very little. I know that their sum must be even. Okay, if this is a sequence of degrees for some graph, then the sum must be even. And there's some work in the 1800s that you can't have too many big ones. If we have too many big ones, then the little ones, there are too many edges to the little ones. I mean, there's some stuff, but not very much. And it was in the 60s. Wow, I should know this date. In the 50s and 60s. There actually, it's two different times that. By the way, of course, you have to sum up to an even number. Okay, that two mathematicians separately, independently, Havel Hakimi. Havel was in one part of the world, Hakimi was in another part of the world. They actually came up with a way to say whether this degree sequence, whether this sequence is realizable as the degrees of a graph. Okay, so here's the key. The vertex of largest degree, if there's a realization, and there may be many realizations. If there's a realization, then there's a realization where the degree of largest degree, the vertex of largest degree is adjacent to the next D1 vertices of largest degree. Okay, so let's go through that for a second. One more time. If there's a realization, any realization, then there's also a realization where the vertex of degree 1 is adjacent to the vertices. This is a vertex of degree D2. This is a vertex of degree D3. This is a vertex of degree D4. And this is a vertex of degree D sub D1 plus 1. So this is subscripts. Let's see. I got to be adjacent to D1 vertices. So notice my vertices are D2, D3, D4, D5, and D1 plus 1. Is that clear? That's D1 edges. So one more time. Havel and Hakimi showed that if there's a realization, then there's a realization where the vertex of largest degree is adjacent to the next largest ones. Okay? So before we actually prove that, let's see how we might apply that. Okay, so let's look on page 85, example 2.5.9. And then we'll come back to 2.5.8. And you're going to stop me when you don't understand something and ask. Okay, so 2.5.9, 44321. 443. Get it quickly. 3221. Okay, notice it's a non-increasing. They're positive integers. So if this is realizable, then I'm gonna say, let's see. Then here's a point. Here is the point x1 has degree 4. So x1 is adjacent to the vertices of degree 4, 3, 2, and 2. Okay, that's what Havel Hakimi says. If this is realizable, then the vertex of largest degree is adjacent to the next largest degrees. 4, 3, 2, 2, 1. And there may be many, 4, 3, 2, 2. There may be many realizations, but one realization puts it adjacent to degree 4, 3, 2, 1. 4, 3, 2, 2. Okay? So now what I'm going to do is, that means that if 4 is adjacent, then now I'm going to look at this graph. So this graph here has degree sequence 3, 2, 1, 1, 1. Right? Why does this graph have degree sequence 3, 2, 1, 1, 1? Because I've pulled this off, and we think that it's adjacent to the vertices of highest degree. So in the whole graph, I'm going to write in a different color. So we think in the original graph, this had degree 4, this had degree 3, this had degree 2, and this had degree 2. Notice there's just one more point, and it still has degree 1. So these are the degrees in the original graph, but in this graph down here, forget this point here, this graph, it now has degree, I'll try blue. So now, in this graph, it has degree 3, 2, 1, 1. So I continue. Of course, at this point, you almost could finish this off. But if 3, 2, 1, 1, 1 exists, then there's a realization where the vertex of degree 3 is adjacent to the next highest degrees. There's a realization where 3 is adjacent to the 3 next highest degrees. So we almost can draw it at this point. Now remember, this degree was 4, so now it has degree 4. This degree was 3, it now has degree 2. So I'm going to need one more there. This had degree 2, we're done. This had degree 2, we're done. And this still has degree 0. Okay? Well, that tells me how to finish it up. If I had red, I got red. Look at that. And now we have a graph. Let's see, the degrees are 4, 4, 3, well, his degree is there. 3, 2, 2, 1. Okay. So it's going backwards of Havel Hakimi, this idea that if there's a realization, then it's adjacent to the next largest degrees. So let me write this out in terms of what it means in terms of the degree sequences. So D1 greater than or equal to D2 greater than or equal to Dn is realizable if and only if. If and only if. Now watch carefully. If and only if. This is the vertex of largest degree. So I'm now going to reduce the next D1 vertices by 1. So if and only if D2 minus 1, D3 minus 1, D sub D1 minus 1. Let's before I go any further, this vertex had to be adjacent to D1 of them. So far, it's like adjacent to this one, this one, this one, this one, this one, and this one. How many is that? So it's adjacent to D2 minus 1, it's adjacent to D3 minus 1, it's adjacent to D1. So I still need one more adjacency. So is that clear? Right? This is only D1 minus 1, so it's adjacent to D sub D1 minus 1. Okay, so now we put this vertex adjacent to D1 vertices. And now I go back, and now the D sub D1 minus 2, D sub D1 minus 3, and so forth. Sorry, you let me do that. This should be pluses. Plus 1, plus 2, plus 3. Right? We're starting with D1, it's going up. It's an increasing sequence. The subscripts are increased, 1, 2, 3, 4, so forth. Okay, so now we can work our way backwards. Okay, so let's look at 2.5.8. So the question is 544,311 graphic. Is there a graph that realizes that degree sequence? 544,311. You're going to stop me if you have questions. Yes.
That's not fair. This will be a -1 and it's D1 plus 2.
So from D2 to D1 plus 1, from here to here, that's D1 things.
Okay.
And we're putting them adjacent to the vertex of highest degree.
Okay.
Okay, and then after that, now they're not adjacent. They're not. Here's D sub 1 plus 2. Here's D sub 1 plus 3.
Oh, I see. Thank you.
Okay. Where was it? Okay, so 2.5.8, 544,311. 544. This is almost too easy. By Havel Hakimi, what can you tell me? 544,311 is realizable. In fact, if and only if what? So let's see. This is D1, this is D2, D3, D4, D5, D6. So I'm going to subtract 1 from the next 6 degrees. Sorry, I'm going to subtract 1 from the next 5 degrees. So 544,311 is realizable if and only if 33200 is realizable. And we're only talking about graphs. Okay, take a minute. Is 33200? The 0, 0, there's not much you can do with that. Those are 2 isolated vertices. Is 332 realizable as a graph? As a graph. Why not?
Well, you can't be negative in that one. The second last one.
Okay, so listen. I like what you said first. The next 3 would have to be. This guy would have to be adjacent to the next 3 vertices. Oh, but wait, it can't be, because this is 0. This is degree 0. So 33200 is not realizable as a graph. As a graph. Okay, so 544,311 is not realizable. Okay, let's get bigger. Okay, so now at your tables, I was going to give 1 to each, but I want you to do page 87, 6 and 7. Boy, those are long. 6 and 7. VI and VII. Yeah. 976. Okay, and 6. Did I say 6 and 7? 866 555 433 32. It's like a telephone. Now, before you even start on these, there are two things that we should be looking at. In number VI, if there aren't 10 points there, if there aren't 10 degrees, there's no way I can have a vertex of degree 9. So you should make sure that, in fact, having a vertex of degree 9 is possible. Okay, that's one. What's the other thing about degree sequences that we know? Not much that we know. What's the other one? Sum is even. So rather than that, summing up a bunch of numbers, so what can you tell me about the parity of the number of odd degrees? What does the word parity mean? Do what? Whether it's odd or even, that's the parity. So what can you tell me about the parity of the number of odd degrees in a degree sequence? The parity.
Even.
It's even. The number of odd degrees must be even. Okay? So let's check that first. 7, 3, 3, 3, 1, 1, 1. Wait a second. 9. 9, 7, 3, 3, 3, 1, 1, 1. So there are 8 odds. Okay, so we're stuck. We're going to have to go through that. We're going to have to actually do something now. Okay, what about the next one? Let's see. I got 5, 5, 5, and 3, 3, 3. So I got 6 odds. So that's not going to help us. So now you got to use Havel Hakimi. So start with these and come up with a smaller degree sequence. Yeah.
Can I ask a question about this Havel Hakimi?
Uh-huh.
So, this thing is about a situation that has to exist, and there's possible it has other.
This is we're certainly okay. So what Havel Hakimi says is, if there's a realization, and there may be many realizations, there is a realization where the vertex of largest degree is adjacent to the next D1 vertices of largest degree. That's all Havel Hakimi is saying. But because of this, it gives you a process to decide whether this is real. So you step by step, after 6 or 7 steps, we should be able to say whether 976, 4333, 111 is realizable.
So if the Havel Hakimi the situation of the Havel-Hakimi is this, so this should be the only one. So if there's only one is this, then it should be the Havel-Hakimi.
It should be the Havel-Hakimi one, right? But rarely do we have a unique realization.
Okay.
Okay. In fact, I think they do raise it in the book that find a degree sequence that has a unique realization. And we've seen a couple on small number vertices, but it doesn't exist too often. Okay. So anybody want to start me off on number 6? So I have a vertex that's going to have degree 9, and I'm not going to draw in 9 edges. This has degree 9, and the nice thing about this graph, if it exists, here are the 9 vertices that it must be adjacent to. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. So here's the graph. What's the remaining degree for these 3? The remaining degree. After this vertex is adjacent to every one of these vertices, what's the degree of these vertices?
0.
0. Is that clear?
Yeah.
They have degree 1 to start with, and they must be adjacent to this 9. Okay, so now what I'm left with is 6, 5, 3, 2, 2, 2. 6, 5, 3, 6, 5, 3, 2, 2, 2. 6, 5, 3, 2, 2, 2. We don't have to go too far. Is there a problem with that?
Yes.
Yeah, what's the problem?
Yes.
What about the 6?
There's not 6.
It's a nice 6.
There's not
But what's
6.
the problem?
There's not 6 non-zero numbers.
There's not 6 non-zero numbers that 6 can be adjacent to. So there's only there's only a total of 6 non-zeros. Okay, one more time. This vertex has to be adjacent to the next 9 degrees. So these are the 9 degrees that it's adjacent to. But this 6 has to be adjacent to the next largest degrees, but there's only 5 that aren't 0. Okay, is that clear? So this degree sequence, no. Okay, that wasn't too bad. What about this one? It's longer. Let's see, I got 3, 6, 9, 11. Is that realizable? Okay, so I'm going to go in steps. If 8, 6, 6, 5, 5, 5, 4, 3, 3, 3, 2 is realizable, then 5, 5, 4, 4, 4, 3, 5, 6, 2, 2, 3, 2 is realizable. One more time. If this is realizable, then this is realizable. Okay? And now I'm going to order the degrees. Okay? I'm going to reorder the degrees. So I'm going to keep it in red. I'm going to have the same degree sequence, 5, 5, 4, 4, 4, 3, 2, 3, 3, 2, 2, 2. Now I want to know, is this degree sequence realizable? Well, if this is realizable, then this vertex of degree 5 must be adjacent to which 5 vertices? The next 5. Okay, so let's try. Can you see that? It's black. Okay. So if this is realizable, then 4, 3, 3, 3, 2, that's 5 vertices, 3, 2, 2, 2 is realizable. Did I get that right? The numbers, there should be one fewer number each time. Okay? The first thing I'm going to do to use Havel-Hakimi is make it in descending order, or non-increasing order. So I'm going to first rewrite this as 4, 3, 3, 3, 3, 2, 2, 2, 2. Okay? All right, continue. So if this is realizable, I'm running over, you're going to have green, if you can see green. So if this is realizable, then the 4 must be adjacent to the next 4 largest degrees. So the 4, so then this must be realizable. Now, you don't have to continue, you don't have to go all the way through this. If at some point you know a graph that attains this degree sequence. Do you know a graph that attains this degree sequence? This is an easy one. Give me a graph that attains this. Okay, so one of these. Okay, or one of these. Okay, right? So it doesn't matter. There is a graph that attains this. There is a graph that attains this. Okay, so I'll give the first one. But it's not unique. Instead of a C8, I could have put 2 C4s. By the way, instead of two C4s, I could have put a C5 and a C3. Okay, so there are many different ways that we now know that this sequence is realizable. And now I'm going to add back. So now I add back my vertex of degree 4. This vertex. So this vertex, doesn't matter which ones, we just know that it has to go to 4 2s. Okay, this vertex of degree 5 has to go to a 4, a 3, a 3, a 3, a 2. Okay, so this vertex, the next vertex of degree 5, has to go to a 4, a 3, 3, 3, and a 2. Let me put the degrees down, just so we're keep track. And it doesn't matter which one, and that's 4. Okay, so this is at this step. Now I'm coming with a vertex of degree 5. That's a red. So here's my vertex of degree 5. And it must be adjacent to 4, 3, 3, 3, 2. 4, 3 3s. Notice there are 4 3s. I can pick any 3 3s I want. And a 2. And a 2. Okay, and now the degree of this vertex is 5. The degree of this vertex, is it okay if I just erase these now? So the degree of this vertex is 5. The degree of this vertex is 4. This vertex is 4. This vertex is 4. This vertex is still 3, 2, 2, 2. Let's see, let's make sure I got that right. The top one is 3. Thank you. That would have been a problem. Okay, let's make sure. 5, 5, 4, 4, 4, 3, 3, 2, 2, 2. 5, 5, 4, 4, 4. It's like a telephone number. 3, 3, 2, 2, 2. 5, 5, 4, 4, 4, 3, 3, 2, 2, 2. Okay, there's my graph. And now I'm going to put in my 8. I'll put my 8 in blue. My 8 in blue. So my 8 goes to 5, 5, 4, 4, 4, 3, 2, 2, 2, 2. Okay, so 5, 5, 4, 4, 4, 3, 2, 2. 5, 5, 4, 4, 4. Okay, there's only 3 4s. That's good. And 4, 4, and now 3, 3, 3, 3, and 3 2s. No, what did I say? Sorry, one, 2 minutes. 5, 5, 4, 4, 4, 3, 2, 3, 3, 3, 2, 2, 2. Oh, well, which one's that? So this is not in order. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8. Yes. Okay, so one more time. I'm putting the blue one in to a 5, 5, 4, 4, 4, 3, 2, 2. 3, 2, 2. And here comes my final degree sequence, which I hope works out. This is still a 2. This is still a 3. This is now 3. This is now 3. This is now 4. This is now 5, 5, 5, 6, and 6, and 8. 866-555-4333-2. Okay, so it's beautiful. It's beautiful the way that is you're supposed to go. You're supposed to go. Wow. Thanks. I appreciate that. Okay, so I know it's a lot of work, but it's just an algorithm. It's just a systematic way of generating these things. It's a lot easier when you come up and find out that it doesn't exist and you don't have to build it. Okay, but Havel Hakimi gives me an automatic system. If we get down to a point where we can get this graph, and I could have kept going, but it's not very interesting. If I get to a point where I can build the graph, then in fact I can build the whole thing. Okay, questions? There's many problems for you to try and play with, and I wanted to. Well, I have 3 minutes. So let me give you a couple problems. So there's the rest of problem 1. So I down to V. So you can have a crack at that. And then what I would like you to look at is 6, 7, 8, and 9. Okay, so that's on page 88 and 89. I would like to prove Havel Hakimi on Tuesday next week, but then I really want to start on chapter 3. Questions? Comments? Anything? Have a nice weekend. Everybody get their homework back? Okay, have a nice weekend.
这件衣服好好看。真累。稍微看这个哇，作业写哗哗的掉，太可怕了。一定要还要做一大堆特别累。他说然后是 economical casting， 然后是的，然后还对，然后还有什么 historical economic thought 更可怕。
Okay, wait a second. Problem 10.
Alex, Julia, Alex, Julia, and Ivan.
Hold on.
So that's another Alexandra, Rodolfo.
Number 10. Oh, construct 2 non-isomorphic irregular graphs of order 10. Okay, so 哦 okay. Those are non-isomorphic, and that's 3 regular. Okay, wait. I'll give you a point. LYU. Okay, so this is a 3 regular graph of order.
知道就很快吧，如果他们知道这套规律的话，过一下就行，然后让他们明天自己去算。
Okay. However, doesn't say connect. 2 non-isomorphic. It's certainly non-isomorphic. Okay. Make sure I get your point. Another one?
Yeah.
Same thing?
I think it was the same, just disconnected.
Okay. It doesn't say connected. What was he thinking? 2 non-isomorphic. Okay. And you choose pick each 2?
我以为你把车停学校了。
这就是学校好了，我怎么能停在 Reading？ 我怎么能停在 Reading？ 不行，停在 Reading， 然后号称就开他们上学。
Okay, I see.
Yeah.
Okay, so I'll give you one.
就开着上学。
Make sure I.
现在还是上学了。
Yeah, that'd be great.
对啊，我住在 Reading。
你不坐校车？